Scientists play a game with the universe and try to figure out its rules. But how do they do it? How can you look at the world and make sense of it? How can you make sure you're right? How do you uncover the laws of nature? Hi, I'm a theoretical physicist and this is a guide on how to make a scientific law. You voted for this and I've talked about this before, but you can watch this video completely on its own. My last video was more of a historical overview, but this video focuses on the process and gives you a better sense for how to actually come up with a good law. In the end, we'll have a rough guide and a cheat code. So, let's jump right into it. Imagine you're playing a game. An overly complex game with different pieces, cards, dice and stuff you've never seen before. And to make it worse, no one told you the rules, and no one will. Everyone else is just as confused as you are. What do? You try to make your own rules, so you can somehow participate or at least admire the game's most brilliant moves. The thing is, you cannot directly see those moves. You can only see the positions of some pieces if you decide to look at them. But the good thing is, you're not alone. There are other scientists that try to figure it out as well. And together you came up with this brilliant tool for looking at the game and making sure you're not being fooled. You called this tool science. It will be our guide to find the laws of nature. We'll come to this in a moment. But first, let's take a look at the game. Looking at the whole game all at once seems to be unnecessarily complex, if not impossible. So instead, we look at one part of the game, at one situation. We look at one part of the world, which we often call a system. So, let's take a close look at this board, this system. Maybe you noticed that each round always starts and ends with the same number of pieces on the black tiles. The kinds of pieces may change, but this number always stays the same. In physics we say this number is conserved. That's interesting. It tells us something about the game without us having to watch it all the time. If this round started with 3 pieces on black tiles, but now you're looking at it and you only find 2, you know that you are missing one. Maybe it is on a different board, or maybe one of the leftover pieces counts as 2. You can learn a lot from this. In particle physics, for example, charges are conserved. If you start with electric charge 0, you should end with electric charge 0. Otherwise, you're missing something. So, conserved numbers are good clues when looking for laws. And of course, our laws cannot violate these conservation principles. Feynman rules, for example, tell us how particles interact, and they only allow interactions where charge is conserved. There are other principles that we want our laws to follow, like the principle of relativity. Physics should not change as long as you're moving at a constant speed into one direction. Or symmetry principles. Basically, they are also telling us that the laws should not change if we change things like positions or times. An apple falls tomorrow the same way it falls today. That's what a physicist calls symmetry. This may seem intuitive, but it has a great implication for our law. To explain this, let me give you an example. Newton's law of gravity is defined in terms of distances, and not absolute positions. This r is the distance between you and Earth's center. So, if we move you and the whole Earth 10 meters to the right, the law still works the same. The distance did not change. This would not work if the law depended on some kind of absolute position. The law can only depend on differences. In physics words, we say Newton's law of gravity is symmetric under space translation. Space translation is moving things whatever meters into whatever direction, and the word symmetric tells us that the law does not change if we do this space translation. Newton's law of gravity is also symmetric under time translation and rotation. As I said, the gravity tomorrow will be the same as today. And well, Earth is rotating the whole time. But as long as your orientation towards Earth's center does not change, the gravity you experience stays the same. Steven Weinberg, one of the founders of the standard model of particle physics, concludes that any symmetry principle is a principle of simplicity. After all, if the laws of nature did depend on how you orient your laboratory, then of course they would have to contain some reference to the orientation of the laboratory relative to something else. And that would be a complication. Well, simplicity is something physicists absolutely love. Actually, that's why I would say physics is a way of cheating in this game. We've already learned quite a bit about the game by looking at it. But we can learn even more if we cheat while we do that. The cheat is to pretend that everything is way simpler than it actually is. What do I mean by that? go and drop your phone so we can test if heavier things fall faster. That would be easier without air resistance. So let's go into vacuum, or we just test things with little air resistance, like round balls with different masses. That's what Galileo did. He slowed the motion down using ramps, and thereby he minimized unwanted influences like air resistance or friction. That is pretty clever. He simplified the situation so that the unwanted influences would not disturb his measurements too much. And then he cheated. He pretended that air resistance was not there at all. Based on that, he drew conclusions. Correct conclusions. The numbers showed that different masses behaved the same way. And they also revealed a pattern between how far a ball had rolled and how long it had been rolling. My numbers are made up, but they could be something like this with the right angle. Importantly, Galileo concluded that the acceleration must be constant. Of course, air resistance was still there, yet Galileo could reveal how objects move without it. That's amazing! Instead of starting from reality in all its complexity, we can just ask what happens in the simplest possible case. And in physics, we are so lucky that the answers to this question are usually incredibly helpful. So, our cheat code is that in idealized situations, physics becomes simple. This works because nature seems to follow simple mathematical laws. So, now I think we're ready to set up a guide to find the laws of the game. We developed some intuition for how parts of the game work. We not only looked at those situations, but also set up simpler versions. Furthermore, we've got some hints from things like conservation principles. We also kinda know what the rules of the game should look like. First of all, they should be simple. Maybe because we believe that nature follows simple laws, or maybe because it's just the most convenient thing to do for us. I mean, after all, we'll never know if we really discovered a rule from the actual rule set. All we can hope for is to come up with rules that let us somehow participate in the game. So, we might as well try to find simple rules. And even if nature does not follow simple laws, simple equations are easier to test. So we can rule them out first before moving on to more complicated explanations. Since the rules are meant to be simple, they should not depend on things like absolute positions or absolute times. Furthermore, they should be consistent with all our other theories, our correct theories. Whereby correct does not mean we are 100% sure, correct means we have enough evidence that supports this theory to feel confident about it. Okay, based on that, we can guess a rule of the game. And thereby, we always try to guess the most likely explanation, keeping in the back of the mind the fact that if this does not work, we must discuss other possibilities. So now we've entered the cycle of how science keeps refining our knowledge. You consider what your guess would imply if it were correct. To do this, you put your guess into a form that lets you make predictions. Then you go and check your predictions against reality. So you make observations and experiments. This way we know whether we're on the right track or if we have to start over. This is how you can make a scientific law. But wait, doing all these experiments and observations to test my guess seems pretty exhausting. Isn't there a way to know whether my guess is promising before I put in all of this work? Is my guess any good? If you think this video is any good, please leave me a like. Thanks a lot, and now back to the question. Feynman answers this with, you can recognize truth by its beauty and simplicity. Yeah, that sounds nice, but it's not so helpful. This one is more helpful. If you're right, usually what happens is that more comes out than goes in. And if you cannot see immediately that it is wrong and it is simpler than it was before, then it is right. The second part emphasizes that your guess should not be complete nonsense, and that it should be easier than whatever we had before. If it's not easier, it's just not very useful, because it will only make playing the game more complicated. That makes sense. What about the first part? More comes out than goes in. Well, Newton's law of gravity describes the attraction between masses, but using this law you can also describe how things fall down and how planets move. There are a lot of possible applications. A lot comes out, but we get even more out of Einstein's general relativity. It also leads to things like black holes or gravitational lensing. It predicts that we can see the light coming from behind a planet because it curves around the planet. This isn't something Einstein thought about at the beginning. It just came out of it. So, how do you find such a universal law? By thinking about what we can't see. I mean, we can only look at certain situations, but we should not limit our thinking to these situations. We must, and we should, and we always do, extend as far as we can beyond what we already know, beyond those ideas that we have already obtained. Only this way you can start with the question of how planets move and end up with the universal law of gravity. And only this way you can conclude that it's the same gravity that holds distant galaxies together, even though they are so big and far away that we can't see them. So, we should not limit ourselves, but try to broaden our horizons. Another way to do that is by switching our perspectives. For example, by considering different theories that describe the same thing. That is super useful when we try to find a new law. You can also guess a new law just from mathematics, or you can enter the cycle at another point, as I showed in this video. Thanks for watching, have a wonderful day!